this module we will cover statistical data integration for small area estimation problem. First, we will start this module by defining what is known as domain, and now I will give you few examples of domain. For example, the target population is the country, the whole nation. Then we can define domain as state, district, municipality, and also it can be demographic domain defined by age, race, sex, etc. Then if we define our target population as state, then the domain could be district, municipality, and so on. We can consider different kinds of population, for example, all business establishment in a state. In that case, a domain of establishment belonging to manufacturing sector in the state could be a domain. Now, we will define small area, also known as small domain. Basically, it is a domain for which limited information or no information is available from the primary source of information. Now, I will give you some examples of small domain. In my first example, it is from Chile. There is a survey called National Socio-Economic Characterization Survey, or briefly known as CACEN. In that CACEN, conducted by Chilean government, there are many municipalities with limited sample or no sample. My second example will be from US survey. It is a National Health Nutrition Examination Survey, where by design of the sample survey, there are few states with no sample in it. So, it is a very extreme example of small area. In the third example, in a nationwide survey, some cells obtained by cross classification of age group, race, gender, even at the national level, it could be a small area. Now, small area goes by different names like local area, local domain, subdomain, small subgroup, and so on. There are classification of domain. One is known as planned domain. This is a domain for which separate samples are planned, and there is another type of domain known as unplanned domain, for which we have not planned any sample. And so, for this kind of domain, sample size could be 0, and this is a very challenging task in small area estimation. I will give you an example here. Age can be considered unplanned domains if samples are obtained from a frame for which we do not have information about the age. There is a big demand for small area estimation, and it is used for regional planning, fund allocation, and so on. The small area estimation is actually not new. We can find examples of small area estimation in 11th century England and 17th century Canada, for example, where small area statistics were produced primarily from census or administrative data aiming at complete enumeration. Now, I will explain the problem with small area estimation if one uses the traditional method that we use for sample surveys, and I will explain this through a simulation example. And for that, we have taken a population, we can call it artificial population, of 431 farms in Australia, and this came from 1988 Australian Agriculture and Grazing Industry Survey carried out by the Australian Bureau of Agriculture and Resource Economists. Here the variable of interest is income from beef cattle. So, what we will do, we will simulate 1000 samples independently from this finite population, and we will study the property of the estimator that is of interest here. So, here we consider sample means, and if we consider a simple random sample, from this finite population, sample mean is the well known Horwitz-Thompson estimator. So, it would be of interest to see how sample mean performs for this simulation experiment. So, what we will do to illustrate the properties of this estimator, we will consider a couple of sample sizes n equal to 10, which we call small sample, and n equal to 50, which is bigger sample, and we will see the effect of change of sample size on the properties of estimator. So, what we did in the next slide, we consider box plots of estimates produced from this 1000 simulated sample. So, if we consider this box plot, for example, here we actually have 1000 estimates of sample mean, and there is a reference line, the blue line, which is the true value, and we know the true value because we know the values of y, the income from the beef, from all the 431 farms. And so, what we observed here is that the mean of the box plot coincide with the true value, and that is understandable because we know from the theory that the sample mean is an unbiased estimator of the true mean. But we also notice that there is a large variability in the 1000 estimates. So, if we are lucky, we may be right on the top of the true value, but for some samples which are not very representative, it may be very far from the true value. So, although sample mean is unbiased, that does not mean that the estimate that you get is identical to the true value. And what we are trying to emphasize here, that the variability of the estimates is important in small area estimation. And if we look, if we compare this box plot, which is for n equal to 10, to the box plot, the third box plot for which n equal to 50, things are getting better in the sense that the variability decreases. We see similar pattern of box plot in the variance estimates too. So, here in the second graph box plot, we plot the variance, and so like the previous one, instead of plotting the means, here we plot the variance estimates. So, we have 1000 variance estimates, and here again the average of all these 1000 variance estimates coincides with the true value, and that is very consistent with the theory because the variance estimate is unbiased. But then we see that this is highly variable. We could be here, which is a very bad estimate, or we can be on the top of the true value. So, from this simulation study, basically what we understand, that unbiasedness is not the only thing, we have to consider the variability. And it also shows in this graph. This graph was plotted from real data from Chilean survey, okay, the survey that I mentioned earlier, the Cassin survey. And in the graph, what we did basically, we plotted the estimate of poverty rate, okay, over time from 2006 to 2013, and the different graph correspond to different municipalities known as comuna in Spanish, and different colors represent different time series plots of poverty rate. And what is observable here, if you look at this graph here, that is for Santiago, and that is a very big comuna or municipality where you have lot of samples, and this graph is very stable over time, and that is because the variability is not much. But we also plotted some graphs, similar graph for other small communas, and here we see that the behavior is quite erratic, and it is not that we have this kind of pattern for the true values, true poverty rate, but we are getting this kind of pattern simply because of the variability in the estimates. Let us explain this graph now. This graph was developed based on the same Chilean data that I talked about in the last graph, but to illustrate a different point. So, let us see what the graph is all about. The x axis here we have communas or municipalities ordered by the sample size. So, here you have the large sample size and here you have small sample size. On the y axis we plot the poverty rate, but this time we are plotting the confidence interval of each communa from 0 to 300 some 40 numbers. We would like to see what happens for large communas. So, these are the large communas. So, you see that here the interval is very small, but here the interval could be very large. And so, here you get lot of information about the parameter of interest, which is the poverty rate, but here we do not get lot of information, because this interval, for example, could be from 0 to 0.4, a wide range, and thus is not very informative. And this is happening because the variability of the poverty rate direct estimate that we get from the sample survey data is very large. And so, we have to do something about it, and so we would like to smooth out the sampling variances by combining information from other sources of data, and that is why data integration is very important. The question is what kind of data we will need to combine with the survey data. That depends on the situation. Sometimes we combine several independent survey data, sometimes we combine a survey data with some administrative records, sometimes we combine survey data with some census records, or we can have any kind of combination of all these databases. Because it is not possible to increase the sample size due to the budgetary restriction. So, the first task would be to identify different databases that we can use or integrate to produce accurate estimates of the quantity that we are interested in. Second thing we have to decide is, once we decide on the different databases, how do we combine those, and we will give you some method of combining, and here is the first one, which we can call synthetic data integration technique. And you will see that this example was given long back in 1950s in the famous book by Hansen et al., and I have given the page number for the reference here. So, what is the problem here? Here we are interested in estimating median number of radio station heard during the day for over 500 counties in the United States. So, we can call these counties small areas. Now, we have to describe what kind of data set we can use for this purpose. First, in that example, they considered a survey done by mail, and this is the mail survey, and in terms of sample size, this is quite big, because for each county they plan for 1000 families. Okay. But the problem is response rate was very low, about 20% on the average, and there is another problem with this data set, and that is known as coverage problem, because they did not have addresses of everybody in the county. So, they were not able to send mail to a representative population, and so the estimate that you get out of it is biased, okay? And that is because of the non-response error, because 20% of the sampled people responded, and also the coverage error problem. So, this kind of error is there, and so although the effective sample size that you get, which is about 200, is large enough, but the estimate will be biased because of these two errors. So, the question is, how do we correct for these biases due to non-response and coverage? So, for that they decided to use another survey which is more organized, and that is the personal interview survey. Okay. And here they have paid lot of attention so that they do not get lot of non-response, and the survey should be good in terms of coverage error. And so, it is an expensive survey. So, they have to limit the sample size, and they could not obtain sample from all the 500 counties. So, what they have decided to do, that they would do only 85 counties because of budgetary reason, and they will try hard to get the accurate estimate of the parameter of interest here, that is the median number of radio station heard. And so, we have 500 counties here, but we can do only 85. Okay. So, they had to be very careful about this data collection. So, what they have done, they have grouped these 500 counties into homogeneous group, so that the counties within a group are more or less the same. And if that be the case, then it would be enough to take a small sample from each group, and in their case they just took one sample. So, from 85 groups they have just 85 counties, and then they collected the data using personal interview survey, which is considered to be more reliable than the mail survey. And in order to take care of the coverage error problem, they did not use the mail list. Instead, they went for area survey, and that way they take care of this thing. So, they got reliable estimates for 85 counties, but the problem is we have to make estimates for all the 500. So, how do you do that? And that is where we have the statistical modeling. So, what they did was very simple actually. They have estimates from both the survey, that is the mail survey and the personal interview survey. For the mail survey we call that x, and for the personal interview survey we call it y. So, we can simply consider a simple linear regression model and fit it using the 85 data points, and that is the regression fitted regression that they got with intercept of 0.52 and the slope of 0.74. And so, they recommended to use the y, that is coming from personal interview survey, for the 85 counties, and for the remaining counties they decided to use this fitted regression. One problem with the synthetic data integration technique that we just described, it does not include the sampling variability of different estimates like y and x that we talked about. Now, we are going to talk about more sophisticated model known as multi-level model, and here I will give just one example of such model. In particular, here we call this area level model. So, here M is the number of small areas or small domains like district or municipalities that we talked about, and I is the index for the small area. Now, level 1 of the modeling, what it does, it captures the sampling variability of the direct estimate, which we call yi, and theta I is the target parameter, for example, true per capita income, true poverty rate, and so on. So, what we assume here in the sampling distribution is yi given theta I is normally distributed with mean theta I and variance psi I. The purpose of level 2 is to link different databases. In Bayesian language it is called prior distribution, but it can be also referred to as linking distribution. So, you see here we assume that theta I, which is the true value that we are interested in, is related to xi, which is the auxiliary variables coming from different databases, and we say that theta I is normally distributed with mean xi prime beta and variability of a. So, this is the sampling distribution and prior distribution in a standard Bayesian model. So, here one thing we will assume that psi I, the variance of the direct estimates, will be known, although in practice they are estimated, and that could be a drawback for this particular model, but it is a simplest small area model for data integration, and we will find it useful to illustrate different concept. So, I will first explain what we mean by Bayes estimator of theta I. What Bayes method does, it updates the prior information described in level 2 in the light of the observed data through what is known as posterior distribution, which is simply the conditional distribution of theta I given the data. In this case data is y1, y2, ym. So, this is the posterior distribution which can be obtained easily from the distribution theory, and it is simply a normal distribution for this example with mean theta I hat b, which has got a formula which is interesting. It is a weighted combination of the direct estimates and the regression estimate of the synthetic estimates, where the weights that we attach to the direct estimate and the synthetic estimates are automatically derived from the Bayesian procedure. So, if we look at the weight, which is bi, also referred to as shrinkage parameter, we will see that when a is very small compared to psi I, that means where we have lot of faith on our prior distribution, then this estimate will be very close to the regression estimate, which is the mean of the prior distribution. On the other hand, if a, the prior variability, is very large compared to the sampling variability psi I, then most of the weight will be going to the direct estimate. And the formula for posterior variance is also interesting. It is 1 minus bi times psi I, and bi being a parameter between 0 to 1, it is a fraction. What it says that it will reduce the variability of the direct estimate by this much. So, it improves the procedure. So, for example, if bi is 0.5, then what we are doing in Bayesian procedure, basically we are giving 50-50 weight to the direct estimate and the synthetic estimate, and in that case we reduce the variability of the direct estimate by half. But unfortunately, we cannot use the Bayes estimate because it involves some parameters like regression coefficient beta and the variance component a, they are unknown. So, we cannot use it. So, what to do in this situation? There are a couple of approaches that I will describe here. One is known as empirical Bayes method, and in this method we will use some kind of classical estimation technique like maximum likelihood, residual maximum likelihood, ANOVA to estimate those parameters, also referred to as hyperparameters. Once we have those parameters, we plug it in the Bayes estimator and we will get the empirical Bayes estimator that way. One thing I would like to say that this empirical Bayes estimation can be also motivated from a classical prediction approach using linear mixed model. To see that, let us consider an alternative interpretation of the model. we can write the Bayesian model as yi equal to theta I plus ei, where theta I is the true value and ei is the error. And then we decompose theta I into xi prime beta plus vi, which is basically the linking model, or that we get a simple form of linear mixed model. Okay. And we are interested in basically theta I, which is xi prime plus beta plus vi, and we can use the classical prediction theory to get the best predictor, also known as BP, and this is identical to the Bayes estimator. And then we can use again the classical method to estimate those parameters. We can call that empirical best estimator. So, we essentially get the same thing from different approaches. An alternative approach is hierarchical Bayes or HB approach. Here, instead of estimating the hyperparameters like beta and A in a classical method, we will put a prior, possibly improper flat prior on beta and A, and then we will find the posterior distribution of the parameters of interest, here theta I, given the data, and then that way we can get rid of the parameters. And then we can consider that final posterior distribution for all inferential purposes. So, I will explain a few of them. For example, if we are interested in point estimators theta I, we will use the mean of the posterior distribution denoted by expected value of theta I given y, and if we apply the standard iterative formula for expectation, then we can find first the expected value of theta I given y and beta and A, and then we take another expectation with respect to the posterior distribution of the hyperparameter. The variance parameter or posterior variance is little bit complicated, because formula for iterative variance is complicated. Basically, we will find the expected value of the conditional variance plus variance of the conditional expectation. To get the credible interval, this is the term of interval estimation in a Bayesian framework. We can simply take the posterior distribution and find the cutoff points for the interval to get the interval, which we can call credible interval. Before concluding this, I would like to talk about few other topics that are of interest. For example, we may be interested in finding hotspot, for example. What are the small areas that exceed some spatial threshold, or what is the worst small area or best small area in terms of poverty rate. And this topic has been considered in Bayesian very well, and I have some references for that. Then there is a question of model selection, because Bayesian is basically model based, and so there are techniques available in model selection. For benchmarking is that in small area estimation we use models, and so when we aggregate them up to a higher level, that may not match with the direct estimator at the higher level. And so there are special techniques of calibration available there. In small area estimation, we use complex model and sophisticated statistical technique. So there is a need for computation, but fortunately there is a software available called SAE package in R. There are a lot of material in small area estimation, and this is becoming very important in different government agencies, and research is ongoing. What I presented is basically a very broad overview of the subject on small area estimation and data integration. And I think with this I would like to conclude my talk. Thank you very much.